Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll review series resonant circuit properties by way of an illustrated example. This lecture operates under the presumption the viewer is intimately familiar with fundamental series resonant circuit properties as illustrated in the series resonance lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, please take the time to do so now. Mastery of series resonance necessitates active participation on your part. As such, I'm encouraging you to please pause the lecture when asked to do so and attempt the example exercises on your own. If your answers don't match those illustrated, feel free to rewind the lecture and correct any mistakes you may have made. Consider the following series circuit consisting of a 50 ohm resistor, a 1.5 microfarad capacitor, and an 80 millihenry inductor. The source is an effective value of 12 volts and an excitation frequency that can be varied up to 1 kilohertz. First question, what's the resonant frequency of this circuit? By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following result. The resonant frequency equals 1 over 2 pi times the square root of the inductance times the capacitance. Substituting our given values into the resonant frequency formula, we find the resonant frequency to equal approximately 459.4 Hz. Let's now determine the electrical properties of this circuit at conditions of resonance. See if you can determine the source current, the voltage across each element, and the apparent real and reactive power experienced by each element at the resonant frequency of 459.4 Hz. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. The complex impedance of the 50 ohm resistor is 50 ohms at an angle of 0 degrees. At an excitation frequency of 459.4 Hz, the complex impedance of the capacitor will be roughly 230.9 ohms at an angle of negative 90 degrees. At an excitation frequency of 459.4 Hz, the complex impedance of the inductor will be roughly 230.9 ohms at an angle of positive 90 degrees. At the resonant frequency of 459.4 Hz, the capacitor and inductor do indeed present impedances of equal magnitude, yet of opposite polarity. The total impedance for this series combination of three elements at the resonant frequency is ZR plus ZC plus ZL. Substituting our given values, we find total impedance to be 50 ohms at an angle of 0 degrees. It appears as if ZC and ZL, being equal in magnitude yet of opposite polarity, effectively cancel each other out, such that the source is under the impression that the circuit consists of only the resistive component. An application of Ohm's law demonstrates source current will be supply voltage over total impedance. Substituting in our given values, we find source current to be 240 milliamperes at an angle of 0 degrees. A phase shift of 0 degrees indicates source current is indeed in phase with supply voltage, as we'd expect for the resonant condition. Given this is a series circuit, it can be said 240 milliamperes at an angle of 0 degrees flows through all three elements forming the series connection. IR equals 240 milliamperes at an angle of 0 degrees, as does IC and IL. An application of Ohm's law demonstrates voltage across the resistor will be equal to the current through it times the resistive impedance. Substituting our given values yields VR to be 12 volts at an angle of 0 degrees. At conditions of resonance, all of supply voltage appears to be dropped across the resistor. Application of the AC power formula demonstrates the resistor will experience 2.9 volt amperes of apparent power, all of which will be directed towards 2.9 watts of real power, and none of it towards a reactive interchange. The resonant condition represents a condition of peak real power delivery. Another application of Ohm's law demonstrates voltage across the capacitor will be equal to the current through it times the capacitive impedance. Substituting in our given values yields VC to be 55.4 volts at an angle of negative 90 degrees. Application of the AC power formula demonstrates the capacitor will experience 13.3 volt amperes of apparent power, none of which will be directed towards real power, and all negative 13.3 VARs will be directed towards a reactive interchange. Similarly, yet another application of AC Ohm's law demonstrates voltage across the inductor will be equal to the current through it times the inductive impedance. Substituting in our given values yields VL to be 55.4 volts at an angle of positive 90 degrees. At the resonant condition, voltage across the inductor appears to be equal in magnitude to the voltage across the capacitor, yet perfectly out of phase with it. Application of the AC power formula demonstrates the inductor will experience 13.3 volt amperes of apparent power, none of which will be directed towards real power, and all positive 13.3 VARs will be directed towards a reactive interchange. Note how the capacitor and inductor experience not only equal and opposite impedance and voltage at the resonant condition, but also equal and opposite amounts of reactive power. This is what defines the resonant condition. Equal and opposite amounts of reactive power cyclically oscillate between the two reactive elements. The source effectively sees only the resistive real portion of the series impedance. Let's take a moment to review the resonant condition. At conditions of resonance, we should expect the following. the impedance magnitude of the capacitor will be equal to that of the inductor, yet of opposite polarity. Total impedance will be equal to solely the resistive component ZR. Source current will be in phase with supply voltage. Voltage across the reactive capacitor and inductor will be equal in magnitude, yet perfectly out of phase with one another. At times, the voltage across these reactive elements can be exceedingly high. Source current will achieve a maximum magnitude at conditions of resonance. Given voltage across the resistor is directly proportional to the current through it, we should also expect voltage across the resistor to peak at the resonant frequency. Finally, given power is the product of voltage and current, this condition of peak voltage and peak current and no phase shift between voltage and current obviously represents a condition of peak real power delivery to the resistor. In summary, only at the desired resonant frequency will this circuit operate at peak power. Any frequency less than or greater than the resonant frequency, in this case 459.4 Hz, all this magic simply will not happen. If we had a lot of time on our hands, we could do a time-consuming frequency sweep of the circuit at different frequencies and plot its performance. Ain't nobody got time for that. Let's see if we can qualify this circuit's resonant condition with a couple measurable quantities, specifically quality factor, bandwidth, and the lower and upper half power frequencies. By all means, pause the lecture and determine these properties on your own. If you're tracking, you should have obtained the following results. There's a couple ways to calculate quality factor. On a basic fundamental level, quality factor compares the reactive power exchange between the reactive elements with that amount of real power dissipated by the circuit. In its purest form, quality factor is calculated as the ratio of reactive power placed in storage over the real power. Given the capacitor and inductor both experience 13.3 VARs of reactive power, and the resistor experiences 2.9 watts of real power, the quality factor of the circuit will be 4.6. This is a reliable method of calculating quality factor. However, it necessitated the time-consuming task of first calculating real and reactive power. A far quicker method of calculating quality factor is the ratio of reactive impedance over resistance. Given the capacitor and inductor both present an impedance of 230.9 ohms at resonance, and the resistor presents a fixed impedance of 50 ohms, the quality factor of the circuit will be 4.6 as previously. Finally, at conditions of resonance, you'll note the voltage across the reactive components will be the source voltage times quality factor. An algebraic manipulation suggests that quality factor will be the voltage across the reactive components over source voltage. As previously, we obtain a quality factor of 4.6. A quality factor of 4.6 represents a reasonably resonant circuit, however, not sufficiently resonant enough for us to use some helpful approximations. As such, we'll have to do a little heavy labor. The bandwidth of this circuit is the resonant frequency divided by quality factor. Substituting in our given values, we obtain a bandwidth of approximately 99.5 Hz. If this circuit had a quality factor of 10 or greater, we could assume the lower and upper half power frequencies are symmetrically distributed about the resonant frequency, but we can't, and we've got to use some really awkward formulas to determine these values. Substituting our given values into these ponderous beasts, we obtain a lower half power frequency of approximately 412.4 Hz and an upper half power frequency of approximately 511.9 Hz. You'll note the span of frequencies between the upper and lower half power frequencies presents a bandwidth of 99.5 Hz as we calculated previously using far simpler methods. Because I simply cannot resist the temptation to poke this thing with a sharp stick, see if we can determine the electrical properties of this circuit at the lower half power frequency, in this case 412.4 Hz. Specifically, see if you can solve for a source current, the voltage across each element, and the apparent real and reactive power experienced by each element at the reduced excitation frequency of 412.4 Hz. You should anticipate some predictable results. Notably, source current will be maximum current divided by square root 2, and real power delivery will be half, hence the name of maximum power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results.